All right. So hopefully everyone can appreciate my title for today. So the plan or the goal for today is just to kind of reiterate what Faustine went over and kind of re-summarize. So talk about ordinal response variables and why we shouldn't use metric models. And then I want to introduce the proportional odds model or the cumulative odds model, which will serve as an alternative to metric models. And hopefully it'll be something that you can use in your research. And then I'm going to talk about how we can use that model and apply it to data. So we're going to be using the data set that Faustine was going to walk through. So that is the plan for today. So if you want to follow along with the lecture, you can just click on this link right here. So last week we talked about dichotomous outcomes, right? So there's two categorical variables or two categorical outcomes, right? So it's either 1 or 0 or, heads or tails. These are not ordered, right? So this week we're going to be talking about categorical variables that are ordered in nature. And these are very popular in psychology and very popular more broadly in the social sciences, right? There's a whole host of examples. And the bread and butter in psychology are Likert items. So a lot of people pronounce it Likert, they're actually pronounced Likert. So hopefully now going forward, you will call them Likert scale items. But Likert scale items are immensely popular in psychology. How many of you in here are using Likert scale items in your research? Yeah, so a lot of people are using Likert scale items. Does everyone at least know what a Likert scale item is? Awesome. Is anyone in here using like just ordinal response? What is an example from your research, Ham?
Actually took some so we have the measure of the 3 necklace you have to learn. So either you get none of them right, all of them right,
Yeah.
2 of them right, 1
Yeah.
of them right.
Yep.
So that's what.
Okay.
1, 2, 3.
Okay. So yeah. So is there any other examples of people using ordinal items or ordinal variables? There's a whole host of examples, right? But I think the Likert items are probably the most popular, at least in psychology, right? So just as an example or a motivating example, so this is my sister-in-law's dog, Honey. And this is her at our wedding several years ago. Adorable. But we give Honey a lot of flack for being very cat-like instead of dog-like. So my sister-in-law went to the shelter and was looking specifically for a cat and came home with this thing. So I might be interested in, the catness of this dog. So as a psychologist, I might have this item, this is a cat, not a dog, question mark, and then I give you 5 responses, right? So 1 is very likely to be a dog, 2 is somewhat likely to be a dog, 3 is as likely to be a cat or a dog, 4 is somewhat likely to be a cat, and then 5 is very likely to be a cat, right? So hopefully you can see that as you progress from 1 to 2 to 3, the catness increases, right? This underlying latent variable of catness increases as you go from 1 to 2 to 3 to 4 to 5, right? So as Faustine talked about, there's lots of different ways that we could analyze this type of data, right? The most common and traditional way is using what's called a metric model. So if you read the Krushke, the Little, and Krushke article for this week, they talk about this as a metric model, but it's basically just parametric statistics, right? So what we would do is we would take all of those ratings, we'd take the average, and then we'd submit them to a t-test or an ANOVA, right? And make inferences based off of that. There's also non-parametric statistics that we could use that don't make those distributional assumptions. And there's also ordinal models, and these actually preserve the ordered nature of the variable. And my hope is at the end of this week that you will shift, your focus from using metric models if you're using these type of ordinal variables to using more ordinal models that best or better fit the data. That's my hope, at least. So if you read the Little and Krushke paper, they analyzed about 68 articles in psychology journals, and they found that every single one of them used metric models to analyze these ordinal variables. So as I said, it is very common and traditional to use this. And as a grad student, as an early career researcher, I wasn't introduced to ordinal models. Everything that we did was metric. We just treated the Likert scales as continuous and ran our traditional analyses on them. And there was lots of arguments being made. If you have more than 4 categories, then it could be considered continuous in nature, and you can just run your models like you normally would. That's what the argument was made. No one wants to give up their t-tests and ANOVAs and regular regressions. They just want to hold on to them for dear life. What are folks doing in your lab, the labs that are using ordinal variables? Are you using ordinal regression? Are you using just regular regression, treating them as continuous? Faustine? So were you ever exposed to ordinal regression before this? Okay, so like just regular like t-tests and ANOVAs.
Yeah, but I feel like predicting identities has the deviate.
Okay. As a predictor variable, right? Yeah. And in that case, like I think it's common to put them in as like a continuous variable, and I think it kind of makes sense. But even then, you can treat them as ordinal. It's wild and crazy out there. Any other folks? Chris, you're like, do you not want to say? Well, hopefully at the end of this week, you will utilize things like ordinal regression to analyze those type of data. That's the hope, right? So as Faustine talked about, there's a whole host of issues with using these metric models for ordinal data, right? So increases type 1, type 2 error. You can have distorted effect sizes and also inversion effects when where you have different signs where the effects go in different directions, right? So lots of bad things can happen when you don't analyze your data properly. And the Little and Kreschke article talked about 3 shortcomings of metric models, and Faustine nicely kind of summarized those issues, but I'm just going to re-summarize those. So one of the assumptions of metric models, right, is that the intervals between values are equidistant. And with ordered response categories, we can't really make that assumption. So this is from the Zhao article that I wanted you guys to read. It looks at bilingualism and ratings. But we can see here that there is unequal distances between these values here, right? Where individuals are maybe more comfortable selecting 2 and 3. The distance seems to be shorter, and 5 and 6, but individuals really don't want to make that distinction between 1 and 2, so the extreme ends, right? People are less likely to maybe select those options. They're not as common as kind of the middle points here, right? So psychologically, these things are not all the same distance, which is important. Metric models can't account for that, but ordinal models can. So responses, so within a metric model, the assumption is normally distributed variables, right? Well, as we can see here, this is from the Paul and Maddie article that I had you guys read. Actually, this is from the Zhao article, sorry. So what we can see here is that the response options are not normally distributed, right? We have kind of these little peaks at each of the response values, right? So on the 7-point scale here, and we see the normal distribution in the background there, right? It is definitely not normally distributed, right? So that's problematic for metric models. And then lastly, metric models treat variance kind of almost as homogeneous, right? So it doesn't take into account the variance between those category cut points or those intervals. And that's problematic too, because it's treating them inappropriately, but ordinal models can. So what we're going to do is we're going to abandon metric models when we're talking about ordinal variables. And what I want to introduce is an alternative model called the proportional odds or the cumulative logit model as a better option to analyze this type of ordered data. So as Faustine talked about, the cumulative model is based on this assumption that we can take these observed values, these observed responses, right, our Likert scale items, right, 1, 2, 3, 4, 5, and we can map them onto some continuous latent variable, a y star or y tilde, right? In our case, with the dog Honey, we can talk about this in terms of Honey's catness, right? How cat-like is honey, right? And I think it's a tenable assumption that what we want to get from these ordered values, right, from this Likert scale item is how cat-like is honey, right? So we make the assumption that this catness variable is normally distributed, as is depicted here, and that we can actually cut up this continuous distribution into bins or thresholds or cut points. Sometimes these are also called tau points. But as you can see here, we can map each of these values to a part or an area under the curve, right? So we see that 1 can be mapped to this part of the curve, 2 can be mapped to this part of the curve with an area under the curve, and then so forth and so on, right? And this is related to what's called the latent variable interpretation. And again, I think it's a reasonable assumption that we can make for these type of variables. So the next question that we have to ask ourselves is, what type of distribution or family can we use to model this data appropriately? So last week I talked about the 3 components of a generalized linear model. Does anyone remember what those 3 components are? What do we need to run a generalized linear model to get the machinery working? No, just like the general components of a generalized linear model. So no assumptions. So we can't use regular GLM, right? The general linear model, right? So what makes it a generalized linear model? I kind of already said the first one. So we need a distribution family, right? We need some way to model the variable, right? We can't use a Gaussian or normal distribution, right? Does anybody remember the second thing we need? Starts with an L.
Length?
Yeah, so you need a link function. And what's the third thing that we need? It's what we know. It's what we're used to. It's what we love. We wish everything could be like it. The linear component, right? The linear model piece. So those are the 3 things that we need for a generalized linear model, right? So in order for us to appropriately analyze this ordered variable, we need a distribution family. And what distribution we're going to use is the cumulative distribution, right? So essentially, we're just going to be adding up probabilities. And this is based off the idea of a cumulative probability, which is the probability of a particular value at that particular value and below it. So what I have here is just a histogram of several different outcomes with the frequency, right? So we're not interested in the probability of a 5. So what we're going to do is we're going to transform this into a cumulative distribution. And if we want to know what the outcome of 5 is, basically what we have to do is we have to take the cumulative probability of 5, and basically it'd be the probability of 5 and everything below it. So if we follow this little line up here, right, this is the cumulative probability of 5. So it's 5 plus 4 plus 3 plus 2 plus 1. That's the cumulative probability of 5. And we could do that for 4, we could do that for 3, 2, and 1. The little red bars here are just the actual probabilities of that particular outcome variable. But again, the idea here is that this cumulative probability just preserves order of the variable, which is what we need, right? Because we have an ordered variable. So we're going to use this cumulative distribution to analyze our data. So the second thing we need is a link function. So there are several different link functions we can use for these type of models, but we're just going to use the logit model, right? And I think that makes it similar to what we talked about last week with logistic regression. So if you remember, for logistic regression, right, we look at the log odds, where the odds is the probability of something happening or whatever is 1 divided by something not happening or whatever is 0, right? With cumulative models, we're going to be using the cumulative odds, which is just the odds of being in category K to below category K, which is referred to as CPK, right? It's just the cumulative probability of being in category K or lower, divided by everything above category K, which we're going to call 1 minus CPK, which is just the probability of being above category K. And similar to logistic regression, we're just going to take the log of the cumulative odds. So it's very similar to logistic regression, but now we're not working with odds, we're working with cumulative odds. So again, trying to make that connection to logistic regression as strong as possible. So as kind of a visualization, we have our cumulative distribution on the left-hand side here, right? So if we want to know what the cumulative probability of 5 is, right, we could just follow this line up and over to the y-axis, and we can get 0.7 is our cumulative probability. And what we can do is we can translate this into a cumulative log odds on the x-axis here, right? So if we follow this, this horizontally and then vertically, we get our log odds of 5 and below, right? And we do that for each outcome variable. And essentially what we end up with are these things called cut points. And the cut points represent the cumulative probability of being at that particular category or below it, right? So when Faustine was talking about these, or when she showed that distribution and all those little cut points, that's essentially what the cut points are. The cumulative probability of being at that category or below it. And what's kind of neat is that we can map our outcome variables in between those cut points. So if you fall between 1 and 2, you respond with a 6. If you respond between these 2 points, you respond with a 5, and so forth and so on. One thing that I didn't talk about, how many cut points do we need? Usually we fit J-1 cut points because we don't need to estimate the last cut point. We get that one for free, right? So if we know all of the cut points if we know all 6 cut points, then we know what the 7th cut point is going to be. So we don't estimate that one. So it's always J-1 cut points. All right, so we have our distribution, we have our link function. So now we need our linear component here. So that's what I have depicted here. So we have on the left-hand side, just our log of the cumulative odds, right? And then on the right-hand side, we have our linear component, right? And what's a little odd about the logit model or the cumulative logit model is that we estimate J-1 equations simultaneously. So that's what I have depicted here. So if we have 6 response categories, then we're going to model 5 equations simultaneously. And these equations are essentially just logistic models that we're fitting here. In each equation, we have an alpha, which is just going to be our intercept. And each equation is going to model a different intercept value. And then hopefully you noticed is that the slope in each of the equations are constant or the same. We're not estimating different slopes for each of the models. The only thing that we're estimating differently in the models is just the intercepts. The slope stays constant across each of the models. And then another thing I wanted to point out is that the intercepts are usually ordered from least to greatest. Looking more into the equations themselves, so the alpha are going to be our intercept or our threshold or our cutoffs, right? This is just the log odds of falling into or below a category, right? The cumulative probability of being at a particular category or below it. That's all that alpha is. Beta is going to be our slope. So like in a standard regression, right? This is constant between the equations. So they're the same. So does anyone notice anything odd about these linear models that we're fitting here, or at least the equation? Yeah, they're subtracted, right? So we're usually used to having them be, added, right? So the reason why these are subtracted is to aid with interpretation. So because there's subtraction in our model, when we look at that coefficient, our slope, we can infer it as being in a higher category. So if we have a higher B value, that means that there's a higher likelihood of being in a higher category. If we just use the normal parameterization with addition, right, with how we're used to being exposed to regression, what that means is that when we have a more positive log odds or a higher log odds, there is a higher probability of being in a lower category, which is not very intuitive, at least to me, right? So higher log odds here, higher probability of being in a lower category, as we can see here. If we have lower log odds, then there's a higher probability of being in a higher category. So we just use that subtraction to kind of flip the interpretation. And we need to be very careful here because different packages will use different parameterizations, which makes things really complicated. So the packages I'm going to be talking about today use the subtraction. So I think it makes things a lot easier to comprehend and wrap our minds around. Make sense so far? For the most part? Good. So as I mentioned, the slope is constant between each of the equations, right? We're not estimating different slopes for each equation. This is based off a critical assumption of the cumulative logit models, and that's proportional odds assumption. So what the proportional odds assumption states is that the slope between categories is going to be constant, or not, it's not going to be changing, right? So there's going to be parallel lines here. And that's critical for interpretation. Our interpretation is that higher B, higher chances of being in higher categories. If our slopes are not constant, then we can't use that interpretation, which just makes things a little bit more complicated. So these models are pretty simple, and I think that they're pretty easy to interpret, but it makes things a little bit more complex when we don't have this proportional odds. And I'm going to show you how we can test for that with actual data. So that's kind of an introduction, kind of re-summarizing what Faustine was talking about. And then now we're going to get into the example that Faustine was going to walk us through so nicely. I should just have you walk us through the example. Are there any questions so far? You guys ready to get into some data and learn how to use these things? So Faustine kind of already talked a little bit about the data set. It's a very popular data set that's circulating around. In future classes, I will probably change this particular example. But for now, I think it's a pretty straightforward, nice example where basically it's a data set with undergraduate students reporting how likely they were to apply to grad school. So it's an ordered variable, unlikely, somewhat likely, very likely. And what we're going to do is go over several different variables to see how that relates to likelihood of applying. So we're going to look at GPA, we're going to look at parent education, and then type of schooling. And we're going to use WebR again so you guys can follow along with me. So we can just click on the code and hopefully this runs the data set. So yeah, so we have the data set here. Awesome. Just going to run this again. So if we look at the proportion of responses in each category, we see that about 35% say somewhat likely to apply, a large majority say a large majority, which is 55%, say unlikely to apply, and then 10% say very unlikely to apply. So let's see how these additional variables affect applying to grad school. So we're going to have to do a few steps to clean up the data to make it usable for analysis. So I am making sure that the pair AD/ED variable is a factor, as well as the public is a factor. And we need to make sure that our data is ordered properly. So there is a function in R called ordered that will order your data in the appropriate way or the appropriate manner. Here we want to make sure that unlikely is first, then somewhat likely, and then very likely. It's very important that you check that these things are coded properly, because then your interpretation is going to be skewed if it is not. So we can see here that it goes from least to greatest, so we're good. Run that again, make sure it ran. Awesome. So let's go ahead and start off with a very simple model. And here we're just going to look at parent education, predicting applying to grad school. And there's two popular packages I guess there's more than two packages, but two popular packages to run ordinal regression models are the ordinal package and the mass package. And we're going to be using the ordinal CLM function to run our ordinal regression models here. If you read the textbook, there are several other packages, and I think they go through two different packages in the textbook. So if you're interested in some other packages to use, the textbook provides those. So what we're going to do is we're going to use the CLM function, and we're just going to fit a regular ordinal regression model, and we're going to use the logit link. So let's go ahead and just run that into the console. And it's not going to allow me to get rid of the summary there. There you go. So if we run the summary, we can see the output here. And on the top, we have just metadata. We have our formula, and then we also have the name of our data set. And then there's other arguments here that we've set. So we're using a logit link. You could also use a probit link if you'd like, and there's some other links as well. Threshold by default is set to flexible. So this is related to what we talked about the equidistant intervals between the categories. When we set this threshold to flexible, which is set by default, we're allowing basically the data to tell us where our cut points are, right? We're not saying that they are equidistant from one another, but you can set that as an argument if you wanted. I think that's a little bit too restrictive, but if you had some theoretical reason why you thought that the actual space between the actual cut points were the same, you could set that as well. For right now, we're just going to use the flexible default argument here. And what's weird about the output from these type of models is that there's two components. There's a coefficients component, and then there's this threshold coefficients component. And I want to go through each of those so we understand what those are. So as I said, two parts, two thresholds, one coefficient. What's up with that? So luckily the coefficients that we get can be interpreted similarly to a logistic regression, right? So we're using that logit link. So this is the estimate, and it is statistically significant. So the estimate is 1.13. So let's go ahead and interpret that estimate here. So for parent ed, right, 0 is that the parent did not go to college, and 1 is that the parent went to college, right? So how do we interpret this estimate here of 1.13? And this is using the logit link.
Is it the log odds then?
Yeah, so it's the log odds, yep. If you want to take a guess on interpretation, so it's the log odds. Get you started. So for a parent who went to college, yeah. So we can say for a parent who went to college, there is an increase in the log odds. If I could spell. Of being in a higher category. So remember our interpretation of the coefficient. Right. So increase in the log odds of being in a higher category. We can say increase of 1.13 in the log odds of being in a higher category. This essentially means that they're more likely to apply to grad school, right? So if you're in a higher category, right, if you go from unlikely to somewhat likely to very likely, you increase the likelihood of applying to grad school, right? So we can also interpret it that way, right? So this is one interpretation, right? So for a parent who went to college, there's an increase of 1.3 in the log odds of being in a higher category. So more likely to apply. So this is how we would interpret our estimate. Again, similar to logistic regression, right? So nothing new. We also have thresholds that, so the thresholds part of the output is something that we should know what they are, but we usually don't interpret them. So in a write-up, we don't talk about the thresholds and we don't give the estimates for the thresholds, but we should know what they are and what they represent. So here in our output, we have two thresholds, right? So J-1 thresholds, right? Each threshold is just the log odds of rating. So the first threshold is the log odds of being unlikely or below, just somewhat likely or unlikely or very likely. And the second threshold is somewhat likely and unlikely compared to very likely, right? So it's 1 versus 2 and 3 when x equals 0, and then 1 and 2 versus 3 when x equals 0. So that's how we interpret these threshold or cutoff values here. As a visualization here, right, we can think of a number line here, right? So we have let's see, excuse my horrible handwriting. So we have unlucky, or there. Let me erase this. Can I erase this? So unlikely, somewhat likely, and then very likely, right? So the first cut point is 0.38, right? So that would like fall right here. Sorry. And then the second cut point is 2.45, and then that would fall right here, right? And that corresponds with our interpretation of these thresholds, right? So the probability of being in this particular category or below, and then this particular cut point, which is 2.45, is the probability of being in somewhat likely and unlikely to very likely, right? So these are what the cut points represent. And again, as I said, we usually don't report these in like a write-up, but they're part of the output. So I want to make sure you guys know what they reference. Questions about the cut points? So we'll get back to the cut points in a bit. So because we have log odds, right, for the coefficients, we can exponentiate them and we can get odds ratios to make the comparisons a little bit more meaningful. Again, all we have to do is just take the exponent of the log odds and we get odds ratios. So that's what I've done here, or that's what's presented here. So I've used the tidy function, and you can use exponentiate equals true, and it will give you the odds ratios. And also too, this will give you the 95% confidence intervals for the odds ratios as well when you do this. If you have the confident int function set to true. But here we can see that our odds ratio is 3.09 here. So how we can interpret this is that if you have a parent that went to college, you're almost 3 times more likely to apply to college, which is a pretty big effect, right? So we can interpret this in terms of odds ratios. We can also take our log odds, our logits, and we can basically transform them into a probability, right? So last week we talked about this logistic transformation function, right? Where we take the exponent of the logit and divide it by 1 plus the exponent of the logit, right? So what I wanted to do is walk through how we can actually kind of pull out these probabilities by hand. I would never ask you to do this, but this is a pretty simple example. And we have functions that will do this for us. But I just wanted to make sure that we kind of understand how to do this. So let's go ahead and pull the predicted probabilities for each of the categories. So let's look at unlikely. And if you have a parent that didn't go to college. So I'm just gonna say no education here. So this is where our intercept values come in handy because we need them to get the predicted probabilities as stated in the formula here. So because the first cut point is the unlikely category and below, that's basically the unlikely condition. So we can use that to get the predicted probability here. So let's just steal that from the output. And we can use the plogis function to get that. So we don't have to add anything here because no education is coded as 0. So the slope is 1.12. So if we just times that by 0, it's just going to cancel out anyway. So we don't really need to include that in the actual output here. So we can get our predicted probability by just using the plogis function, just using the intercept value for the first cut point. What about unlikely educated? So what we have to do here now is we just have to add in our slope value, right? So 1.12, and then we coded that as 1 if you were educated or went to college. That gives us 0.32. What about somewhat likely? Here we're going to have to do some subtraction here. So the second cut point is the cumulative probability of being in the somewhat likely category and below it, right? So what we have to do to get somewhat likely probability is we need to just take the cumulative probability of the second cut point and subtract it from the first cut point, and that will give us the somewhat likely predicted probability. So let's go ahead and do that. So I'm just taking the second cut point and subtracting that from the first. And this is for the no ed condition. So that would be for the somewhat likely no education condition. And then we could do the same thing for the education condition. And here we just add in our slope of 1.12 times 1. Right. And we get our predicted probability for being in that category. And then now we have very likely. So the last category for a cumulative probability is going to always be 1. So what we can do to get the no education very likely probability is just take 1 minus the second cut point. And this will give us the predicted probability, if you don't have a parent that's educated, to respond very likely to apply. And we get about 0.08. And then if we wanted the very likely educated, we just have to add in the slope value. And this will give us 0.21. So this is kind of how we can calculate these things by hand. This is a very simple example. I would never ask you to do this because we have functions that will do this for us. And that's what I have highlighted on the next slide here. So this is using the marginal effects package. There's a function called marginal means. And we can see that what we estimated by hand is what it does in 1 line of code. So why are we going to waste our time doing this by hand, right? But just to kind of get a feel conceptually of what's going on here. So again, these are what we estimated. These are the predicted probabilities for each of the conditions for a parent who's educated and not. So are there any questions about that so far? Pretty straightforward. So in terms of visualizations, it's quite common to visualize these type of models using predicted probabilities. And what I have highlighted here is a function from marginal effects again. I really love this package, so I'm glad I'm getting to use it more. They have a function called plot predictions that will essentially output something that looks like this. So this is the predicted probability in each of the categories by parent education. And you can also modify these using ggplot syntax to make it a little bit prettier. So how can I make this particular plot better? So I was pretty lazy when I created these things. What do you think I should do to make this plot a little bit better? Just for fun.
Switch the zeros and ones to.
Yep. To actual categories. Yep. What else? Yes, correct. Yep. So these are not in order. I don't know why it doesn't put them in order, but yeah, so it should go unlikely, somewhat likely, very likely, just the little things. So this is what you get just by running the actual function. So it's important to, actually critically assess what it's outputting and make changes based off of that. Yeah. But again, for 1 line of code, I think that it produces some decent looking graphs and they're customizable. So I think it's pretty cool. So we can also talk about these things in terms of marginal effects. And again, we can use marginal effects package and the average comparisons function, and we can get the actual risk difference between the parent educated and no parent educated conditions for each of the groups, right? So we can look here, right, for somewhat likely. If you have a parent that is educated or went to college, you're 14% more likely to say that you're going to be somewhat likely to apply. If you have a parent that went to college, you're 27% less likely to respond that you're unlikely to apply to college. And then if you have a parent that is educated or went to college, you're 13% more likely to say you're very likely to apply. So it makes these things a little bit more concrete. And again, 1 line of code and you can get these type of things, which I think is really cool and neat. So I talked about the proportional odds assumption. Does someone want to remind us what the proportional odds assumption is again? Yep, exactly. Yep. So the slopes are constant, which means that between the category cut points, the slope is the same. So the lines should be parallel to one another. And one way that we can test that is with the Brandt test. And basically what the Brandt test is doing is just basically a chi-square test where it's comparing a model that has this proportional odds assumption, so just one slope, versus a model with multiple slopes. And there's a function called Brandt test, pretty intuitive. You feed in your model and it's going to output the results for those chi-square tests. And we want our chi-square test to be non-significant, and it is for this particular model. So you'll see this omnibus row here. That means the model with all of your predictor variables in it. And here we only have one predictor variable, so these are the same. But this would be evidence that we have proportional odds. Well, what the heck do we do if we don't have proportional odds? So there are several things that we can do. One would be to use a multinomial regression, which we're going to talk about next week, where we can use the lowest category as our reference or baseline, and then compare each successive category to that baseline. We could also fit what's called an adjacent category model, where we compare category 1 to 2, and then compare category 2 to 3, and then compare category 3 to 4. So kind of this sequential type of model. And then your book talks about this thing called non-proportional odds, or NPO model, that we can fit. And what I wanted to do is highlight how we can fit something like that. So there's a different package that we have to use for that, and this is from VGAM, and there's a function called VGLM, and we can just fit our model, and we can set this parallel function or this parallel argument to false. And what it's going to do is you're going to get some output that looks like this. And what we can see here is we have our intercept values, right? So if we have 3 categories, we only have 2 intercept or cut points. But we don't only have one slope now, we have 2 slopes. So we have the slope for the first cut point and then the slope for the second cut point. So again, I just want to highlight that this allows the slopes to vary or differ between those categories. That's all that this is doing. And you can interpret the coefficients exactly the same way that you would with a regular ordinal regression model. But when you hear things about non-proportional odds, this is essentially what it's stating, right? That the slopes are allowed to differ between those categories. And if it's reasonable to assume this, maybe you should always run something like this, but the actual cumulative logit model is just so simple to use, and also just test if there's actual proportional odds. And then there's other things that you can do if that's violated. All right, so I wanted to spend a little bit of time talking about ordinal assumptions. So it's really the wild, wild west when we start talking about generalized linear models or any complex models in terms of assumptions. And that's because there's so many different ways that we can quantify like what a residual is in these models. But I did stumble upon a package called the SURE package that uses these things called surrogate residuals. And basically the basic idea behind these is that it's based on continuous residuals. So it takes this ordinal variable and then maps them onto a continuous space essentially. And when we do this, we can test for things like normality with our QQ plot, linearity, and homoscedasticity, right? And unfortunately, you can't take a CLM model and throw it into Easy Stats Up. Breaks my heart to say that. I wish that they would create something for it, but they have nothing. So we just have to use other avenues. But this seems to be a good way to test some of the assumptions. And again, you can't even test for multicollinearity with Easy Stats, so you have to go the old way and just look at correlations between the variables, right? So a Spearman rank correlation would work for these type of variables. But I have code in the Quarto document that shows you how you can run these different assumption checks. But this is our model here, and what we can see for our QQ plot is that all of the dots fall on the line, which is good, right? So normality seems to not be violated. This particular plot is to test for linearity. So kind of very similar to the check model function from Easy Stats, right? Where if we want to draw a horizontal line at the 0 point, they should roughly be similar. So linearity seems to be not violated here as well. And then the plot on the bottom is basically testing for homogeneity. So we have these box plots here, and they should be roughly overlapping one another here because we want equal variance. So these are fairly similar to one another. So we can say that we have homogeneity or constant variance here. And as I said before, the code for this is in the actual Cordo document. So if you have to do this for, let's say, on Wednesday, that's where you can find the code for this. All right. So now let's get a little bit more complicated and let's add some more variables into our model. So let's go ahead and add in public. So did you go to a public school or a private school? And let's add in GPA to our model. So let's go ahead and run that model here. And this is just giving us the coefficients, not the thresholds. So we're not going to interpret the parent education one because we already did, but let's go ahead and interpret public and GPA. So, and the reason why I wanted to interpret public, and we'll notice that the p-value is not statistically significant, but we're going to interpret it anyways. You shouldn't do this in practice, but for demonstrative purposes, we're just going to interpret it. So how do we interpret this estimate of negative 0.06? So public is labeled as 1 and private is labeled as 0. Yes, correct. Good. Yeah, good, Kenan. Yes. So we could just say for those that went to public school, there is a decrease in the log odds of being in a higher category of 0.06. Right. So that's essentially how we would interpret the log odds of that, right? What do we do if we take the exponent of this value? What is the exponent of negative 0.06? Someone want to really do that? Just enter it into the console. .94, right? What would be the percentage decrease in that case? %? Round? Did anyone do it? So do you guys remember how to take an odds ratio and then turn it into a percentage increase or decrease? So there's a 6% decrease in the odds of being in a higher category if you went to public school compared to if you went to private school. Right? So I think that it's a little bit more intuitive to talk about odds ratios in terms of like percentage increases and decreases. We could definitely talk about it in terms of the odds ratio itself, but I think talking about a decrease or increase is a little bit more intuitive. So what about GPA? So we could say an increase in GPA, right, leads to a 0.6 or 0.2 increase in the log odds of being in a higher category, right? So more likely to apply. What is the odds ratio of that? And then what's the actual increase, the percentage increase in the odds ratio? 65%. Right? So the odds ratio of that is 1.85, right? So about 85 or 86%, right? So your 80, so increases. So if you have an increase in GPA, you are 86 times more likely to apply to grad school. Is how we can infer that, or the odds are 86% compared to if you have a decrease in GPA. So we can test the proportional odds assumption for this model by using the Brandt test again. So again, we have more predictors now. The omnibus test is with all the predictors, and then the individual predictors, allowing the slopes to vary. Here, the p-values are all greater than 0.05, right? So we don't really have any issues here. So the proportional odds assumption holds for the most part. So there's lots of different ways that we can visualize like ordinal variables. So this is one way we can visualize continuous predictors. This is with a stacked area plot that I kind of like. So this is kind of ugly, but I wanted to highlight this effects package. So with one line of code, you can create something quick and dirty like this. And I think that this is a nice way to visualize these type of effects, right? Where you can kind of see that lower GPA individuals are more likely to say they're unlikely to apply. And then as GPA increases, we can kind of see that the area widens for somewhat likely and very likely. So I think that this is a good visualization for these type of models. These can be modified in ggplot. So that's probably what I would suggest. But for a quick and dirty plot, I think it looks pretty nice. We can also do these stacked plots, right? So we did that last week. These are ugly. Don't put this in a paper or in a report. But again, one line of code and you could get something like this, which I think is pretty nice. So let's add in an extra level of complexity to our model. Let's just add in an interaction real quick. Let's look at the parent education times GPA interaction. And let's go ahead and just run the model. So we'll see here that the p-value is not statistically significant for the interaction. So let's go ahead and actually just test that. So let's use likelihood ratio tests and do model comparisons here. So is a model with just the main effects better than a model with an interaction term in it? So again, we've been using the ANOVA function here to test this. And this is the output of that. And what we see is that the chi-square statistic is not statistically significant. So what we can conclude from this is that the main effects model is probably the model we should go with. We don't need the model with the interaction term in it. We can also test main effects and interactions for these type of models, especially if we have lots of variables in our model. So lots of categorical variables, lots of continuous variables. We can use the ANOVA function and we can just feed it in our model and it will give us this likelihood ratio test, right? So we see here that there's no effect of public, no effect of parent education, there is an effect of GPA, and there's no interaction in our model here. So this is another way. If we don't want to use the summary output, we can just use the ANOVA function to do our significance tests if we wanted to. And remember, if you're testing interactions, use type 3 sums of squares. So you can set the types here. If you're going to use a main effects model, type 2. Do not use type 1. So we can actually visualize our interaction here. This is with the plot predictions function for marginal effects. Again, one line of code, and it could produce something pretty nice like this that you can then modify with ggplot syntax. But hopefully we can see here that the slopes are essentially parallel, right? There doesn't really seem to be any type of interaction going on here within the categories. But this is one way that we can visualize it. So if we were going to use the main effects route where we're going to use the ANOVA function, we can follow those tests up with m-means, right? So pairwise comparisons. And I just wanted to highlight how we would do this. So what we're interested here are results on the logit scale, which is the latent scale here. We're not as interested in the probability scale, but you might have theoretical reasons why you want to look at probabilities. And if that's the case, then you can look at those comparisons using something like marginal effects. Here, we're just going to stay on the logit scale because it's a lot easier because things are continuous and we're comfortable in that space. But we can use m-means to just get our pairwise comparisons here. And then we can use those to make our interpretations, right? So we can do that for the parent education variable and also the public variable here. So just wanted to highlight that. And then if we wanted to test our interaction here, we can use the mtrends function from m-means, and we can look at the simple slopes analysis, where we can look at the actual slope within parent education and when the parent is not educated or didn't go to college here, right? So we can get our trend or our slope here, and then we also get our interaction term here, which we know is not statistically significant. But this is how we can do those interaction tests within these type of models. And then I want to talk a little bit about the effects package again, because we can map out the interaction on the latent scale here. And we could probably do this a lot nicer in something like ggplot or some other packages. But what I like about this, again, is one line of code, but also it includes the cut points here on the actual figure itself. I mean, again, we could probably do that in ggplot as well, but again, quick and dirty. So this is on the latent scale, right? So the y-axis here is going to be our logits, but we can kind of see, again, as you increase or go up, you're more likely to be in the higher categories here. So this is kind of just a visualization of kind of the latent scale that we're talking about. So we can also look at marginal effects for larger models. This is just using average comparisons like we've been using, and we get the probability on each group. So for GPA, parent education, and public. So as you can see here. In terms of model fit, we can calculate an R-squared to determine how well our model fits. Here I'm just using the McFadden R-squared, and the R-squared is about 0.03, which is pretty small. So it's a poorly fit model for sure. What I have here is just a sample write-up. So how we might go about writing up this ordinal regression model. So I say a proportional odds model was estimated to investigate parent education, GPA, and public schooling that influence whether undergrads apply to grad school. So the overall model fit was poor. I said parent education predicted the likelihood of applying to grad school. I have my log odds here, and then I also have my odds ratio. And students with parents that went to college increased the odds of applying to grad school by about 206%. Or we can say that increased the likelihood, or they're three times more likely to apply to grad school. Whether parents went to public or private school didn't seem to affect whether students apply to grad school. And then GPA was a significant predictor. So each point increase on GPA was associated with an 84% increase in the odds of applying to college. We could also add in our risk differences too, if we wanted to, but that's not fairly common in these type of analyses. But we should probably include our risk differences or probability differences, right, for each of the categories. But I think we can highlight that in our visualizations. That gives the probability differences between the categories themselves. And the last thing I wanted to talk about is that if we had more complicated designs, so if we're doing repeated measures or we have multi-level data, we can use the ordinal package to fit those type of models, and we just have to use the CLMM function here. And we can use the same syntax that we'd use for the LMER, and we can fit multi-level ordinal regression models here if we have something a little bit more complex. So it's fairly easy to scale up with these type of models. So that is all that I have. So Wednesday is probably one of my favorite labs because we're using one of my favorite data sets. So is anyone familiar with Great British Bake Off? Yes, so I have a Great British Bake Off data set, and we're going to look at ranking in technical and what factors influence whether someone wins in technical. So it's a fun data set. I like it at least. So that's what we're going to do on Wednesday to kind of apply some of this stuff. So are there any questions about ordinal regression? Are you guys more likely to use it now? Yes? Thumbs up if you're using ordinal variables. Definitely should be using ordinal regression for sure. But yeah, so if you guys don't have any questions, you guys are free to go.